Let me begin with a word of prayer here. All right, so I'll begin. Heavenly Father, we thank you for this day again. I thank you for your creation, for these students, and I just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So let me solve these problems right quick. So problem 1, we're supposed to find the orthogonal trajectories to dy dx equals to minus x over y. So find orthogonal trajectories to dy dx equals, what did I just say, minus x over y, right? So you're looking for curves which are perpendicular to the solutions of this differential equation, right? So what that means is we need to solve not the problem that's given, but the one which has the negative reciprocal slopes of what you're given. Now that is just y over x. And so what you got yourself into here is dy over y is equal to dx over x. Integrate that. Log absolute value of y equals log absolute value of x plus a constant, which gives us the absolute value of y is equal to e to the c times e to the log the absolute value of x, also known as plus or minus, well, also known as e to the c times the absolute value of x. And from this we find y is equal to like mx, where m equals to 0 is technically an extraneous solution to the separation of variables method because we divide by 0 when m equal to 0 there. But nevertheless, if you go back to the original problem, y equal to 0 is a solution to this problem, right? Those are orthogonal trajectories. Now if I solve this, which some of you doubtless did, you've got x dx plus y dy equals to 0, which the right way to solve this is to tilt your head, squint, and go, well, that's x squared plus y squared 1/2, the differential all that equal to 0. So the solution here is x squared plus y squared equal to, like r squared, which of course is a family of circles concentric about the origin, the orthogonal trajectories of which are the lines that go through the origin, right? So this, of course, not solution, actual solution. Still, hey guys, if you found this, you're doing something right? Or if you had x squared plus y squared over 2 equals to a constant, that's also cool. But, I write it that way because then I know what I'm doing. I recognize the problem. So this is problem 1 from quiz 3. So just to recap, how do you find orthogonal trajectories for a given differential equation? If you have it in the form dy dx equals to something, you solve dy dx equals to minus 1 over that something. That gives you the so-called orthogonal trajectories, right? So there's that. Now problem 2 here, if I can find my marker. Problem 2 was to find the velocity as a function of time. So, and I guess you could have rightly asked me, what are you talking about? But it was assumed for a mass not equal to 0 because we have not talked about how to find the velocity of a massless particle, and we're not going to. Although that's kind of boring. It's just v equals to a constant c, or minus c, I guess I wanted to mention. So anyway, we got m dv dt, that's ma, is equal to minus beta v squared. But in my defense, we did do this last class. But instead of v squared, we had v, right? Wrong? What did I do last class? I had v, okay. So, great, separate. Integrate. I would integrate from v0 to vf, t0 to tf. What's that give me? Well, it gives me minus 1 over vf plus 1 over v0 is equal to minus beta over m times tf minus t naught, which I can solve. So I'm going to set vf equals to v, and I'm going to set tf equals to t for the sake of making it look pretty. And yeah, so that gives me 1 over v is equal to 1 over v naught plus beta over m times t minus t naught, I think. I gotta be careful. And let me take a step back here and think about my signs. Do you guys remember that movie? No? Before your time, right? Let's see here. 1 over v is 1 over v naught. Yeah, I think we're good. And then to solve for v, flippity floppity, this is going to give me v is 1 over v naught plus beta over m times t minus t naught. Right? Which, if you like, you could clean up. This is v naught over 1 plus beta v naught over m. Hold on a second here. Yeah, we're fine. T minus T naught, which I could also like simplify again, but I think, you know what, there we go. Fine. I mean, there's a lot of different answers I will take for full credit here, guys, but here's a slightly prettier way to write it. Yeah.
Did you get a haircut?
I did? Yeah, I guess so, yeah. So if I ask long enough, I'll get one. Let's see here, so yeah.
Should the T's, why are they denominated there other than
Oh yeah, I think something went wrong right here, right?
and you divide, you just get it right here.
This felt wrong. So yeah, I think the wrong step was here, and then I just carried it through. So let me fix it in red. Thank you. I felt like something was wrong. Thank you, thank you, thank you. As I warned you guys, I will make mistakes at this time in the morning. Like, I'll make the most hilarious mistakes at this time as compared to other times. Like this is, you're gonna get some quality mistakes at this hour. Let's see here, so this is one of them. Yeah, that's supposed to be up there. If we did dimensional analysis, we would also have figured this out, you know, that that was supposed to be like this. And let me talk about that dimensional analysis just for a second here. So like beta times v naught beta, if we look at like, well, it's, anyway, that's what it is. So, but you could go through and like figure out like the kilogram meters per second for beta, and then reason through that this has to be a dimensionless quantity, which forces us to put this as opposed to what I had before, you know. But anyway, other questions? All right, so now that we've done that, let's take this example and take it up a notch. So what if happens with problem 2? What if instead of saying the velocity is a function of time, I would like to find the velocity, say, as a function of position? What would I do then? Ew. Oh man, did I? Oh, phew. For a second I thought I had no juice. All right, so example 2 continued, well, problem 2 continued. Find velocity as function of position. Can't spell. Position, let's say x. We'll assume that dv, excuse me, we're going to assume that v is dx dt, right? So one way we could do this would be to like take my velocity function, which was what? After we worked out our demons, so to speak here. 1 plus beta v naught over m times t minus t naught, right? Wasn't that the formula I found at the end? After you guys fixed it for me. Thank you. And v is what? V is dx dt, right? So we could answer another question that I didn't ask yet, but it's an interesting question to ask, which is what is the position as a function of time, right? How would we find the position as a function of time? Well, we just gives us that x, is equal to x naught plus the integral, from t naught to t of, v naught d tau over 1 plus beta v naught over m tau minus t naught. All right, so what I've done is I've used like a theorem of calculus 1. And I changed the velocity at time t to a velocity at time tau, so I can do the integration to t. So this is the kind of thing you're going to need to do if you don't introduce the t sub f like I did in the previous calculation. Like I introduced the t sub f, so I didn't have to do integration over tau. But if I don't introduce the final time and the final position, I can do like this. But if I do that, I need to like swap out the integration variable. Instead of t, I have to use tau because t has a fixed but arbitrary meaning here. And then you can do this. What is this? Well, x naught plus v naught times m over beta v naught, natural log of the absolute value of t minus t naught. Oops. Oof. Oh, phew. Yowzers, I was like, oh man, this is bad. This is 0 when I plug in t naught, But what am I not doing correctly? I need to make a u equals 1 plus beta v naught over m times tau minus t naught substitution, you see? And so my du is beta v naught over m d tau. So when I solve for d tau, it gives me an m over v naught beta, all right? But I'm supposed to have the natural log of the absolute value of u for my antiderivative, which gives me, I'll write down a step here, evaluated from, let's see here, what's u of t naught? It's 1. And what's u of t? Well, it's, so we end up with from 1 to 1 plus beta v naught over m t minus t naught. All right, great. So what we have then is x naught plus v naught m over beta v naught natural log the absolute value of 1 plus beta v naught over m times t minus t naught. So there you go. That, my friends, is the position as a function of time for this problem. In terms of the initial position x naught, the initial velocity v naught, based at an arbitrary time t naught. Okay. What was natural log of 1? It's 0, right? So that's why that's gone. Okay. Now that wasn't the question I asked. I didn't ask us to find the position as a function of time. What did I ask us to do? Find the velocity as a function of position, right? So how would I find that now? With what's on the board? What do you need to do to find the velocity as a function of position? I mean, I've got velocity as position as a function of time here. I've got velocity as a function of time over here. We don't care about time, right? So what we could do is just do what? Solve this for t, then plug into, v equals to v naught over 1 plus beta over m t minus t naught, I guess, right? Is that what I had? Oh, beta v naught. You guys can do algebra, right? So you could do this, yeah? But should you do it? The answer is decidedly no. This is the wrong way to do it. There is a better way. A way with calculus. So instead of actually doing what I just said, we will instead solve a related differential equation and find velocity as a function of position directly. So here's how you do that. A better way. I have no regrets. Like, it's good for us to calculate position as a function of time, and that's why I did that, okay? It wasn't an accident, although it was to make this point. So here's the deal. If the acceleration for a one-dimensional problem is dv dt, right? Then we can swap that out for dv dx by the chain rule. See, what this is dx dt, dv dx. This is the one-dimensional chain rule. This is a one-dimensional problem. I can get away with this. You'd be like, well, your velocity is really no longer the velocity. You should use a different symbol, because now it's a velocity as a function of x. But no, you guys won't say that, because you're engineers, and you don't do that kind of thing to me. And the math majors are also not that careful. So I'm really, unless there's another math professor here, I'm probably fine. OK, we're good. So this is v dv dx, which I love to say. v dv dx, v dv dx. It just feels right. So v dv dx is equal to what? Well, we've got ma is equal to mv dv dx. And that, my friends, is equal to what was given. Oh no, it's gone. Ah, minus beta v squared, right? That was the deal, wasn't it? Yeah? Now, solve. That's way easier than doing the algebra solving for t and plugging into the other equation, right? Like way, way easier. So here we go. This gives us dv over v is equal to minus beta over m dx, I believe. Separate, and then I'll integrate. And again, I would suggest using the xf x naught thing, because invariably you guys will not do the tau thing correctly, and it's just better to do the vf and v naught business. So over here, correspondingly x0 and xf. So what that gives me is the natural log of the absolute value of vf minus the natural log of the absolute value of v naught. My apologies for this hideous Carolina blue. Equals to minus beta over m. It's not the color that's hideous, it's what it represents. But x0, x naught. Sorry, none of you really know what Carolina is, nor care. But you should understand, I went to NC State, so it's like a law. I have to have a deep-seated and residing hatred of UNC Chapel Hill. What's that?
I said it's a little dark for Carolina blue.
It's true. So maybe it's okay. But you can't be too careful. So, so this is the log of the quotient of vf by v naught is equal to minus beta over m xf of minus x naught, which I'll continue working over here. So that gives me vf over v naught. Actually, let's say v over v naught. Absolute value of v over v naught is equal to e to the minus beta x minus x naught over m, which then gives me v is equal to v naught e to the minus beta x minus x naught over m. And there you go. That's the velocity as a function of position, if I haven't made a mistake. So what I did in the last step there was I set vf equal to v, and I set v naught, I set xf equal to x, okay? And I mean, I exponentiated both sides, right? E to the natural log is the thing inside the natural log. Are we good? So if I ask you to find the velocity as a function of position, do not do what I started to do. Instead, use the acceleration as v dv dx trick. That will make things much easier for you. All right? Okay. Let's see here. Let me show you guys some examples in the notes that are a little bit more complicated that would take me a long time to write out in class, but I think are worth looking at together. So let's do that. So listen, guys, the reason I give you quizzes, I mean, there's two reasons. One, I want you to come to class. Two, more importantly, I want to give you some heads up if you're not understanding things, right? And understanding me do something is very different than doing it yourself, right? Like really, really different. And as such, these quizzes will help you gauge, you know, how you're doing. Because there is a test coming up, right? And so this gives you some window as to where you are for that test. So like the quiz I gave you guys Friday, I was somewhat picky with the grading, sort of test level pickiness, give or take. So if it looks to me like you don't really know what you're doing and you're just telling me nonsense, like I'm going to take most of the points. But if you're kind of close, but you just made a kind of a procedural error, then I'm a little bit more sympathetic. So an example of that would be problem 1. Some of you had everything right, except you didn't put the minus here. I think I took a half off for that. If you didn't have the minus and you had a wrong number over here or didn't find the number, I took off 1 out of the 3. So the point here, and I made this point in class before the quiz, right, is that if the y in the point is negative, you can't attain such a point by using a positive square root, right? So yes, the algebra allows for plus or minus, but you have to make a choice. And if I give you a negative data point in this particular problem, you must choose the minus as well as selecting the 2, right? The larger point is you need to think through the algebra of fitting the initial conditions if initial conditions are given, all right? That's all. But otherwise, I think most people at least had something here, you know? Yeah? Now, for problem 2, this was just like straight integrating factor method. And some of you got it and some of you did not. Of those of you who did not and attempted the method, maybe you like stopped here and tried to do something like that. That's not going to work. Like you need to do the algebraic simplification on the integrating factor, and you need to do it correctly, otherwise things aren't going to work. You need to think through this step. Some of you like found some integrating factor and you pretended this happened, but it didn't happen. I don't give a lot of credit for that. If you're not thinking through this, you find a wrong integrating factor and you're just trying to like, well, it's integrating factor method, so I do this. You're not thinking through it. I take a lot of points off because I want you to be thinking through the method. So I would rather have a solution that says, you know, this integrating factor didn't work, I miscalculated it, you know, as opposed to pretending it works and doing some integration which is nonsensical. I'd rather just have a correct solution though. Okay, so like, but anyway, so there's this one. And then on the back here, a lot of people got this. So the stuff I have at the start, you don't need to do. I didn't take off points if you didn't do it. This is for the sake of like full discussion, right? Like, so my P and my Q are such that they satisfy the closed condition, and that means that it's exact, meaning that there exists a potential function. And I will post this solution in Canvas, don't worry. Now the solution to the quiz I went over today, I probably won't post in Canvas because I went over it for you guys in class, but this one I actually wrote out and I have a PDF of I'll post in Canvas. Maybe I should write out the other one. I don't know. No, I gave it to you in class. It's enough. Sorry. So I integrate the first one with respect to x, it gives me a constant y, then I plug it into the second one, and when I do that, the certain terms cancel out, and I end up with the same term here both places, which eventually gives me that partial c1 partial y is equal to e to the minus y, but partial c1 is really a total derivative because c1 just depends on y, which brings me to this dc1 dy equal to e to the minus y, which then I integrate, and lo and behold, I get the boxed equation. Now, I don't expect you to do it that way. I just did it this way because I've done it the other way a bunch of times in class, okay? The other way is just to do what? Integrate the p part with respect to x, integrate the q part with respect to y, and merge them. Now, some of you did that but didn't merge correctly. You kept 2 copies of the common term. You can't do that. If there's like a, you end up getting the sine xy term from both the integration of the p term and the integration of the q term, right? You only need one. Just one of these will produce both of those terms in the differential. And then another person didn't put this equals to c. They just put big fxy equal to that. Well, that's lovely, but that's not the solution. The solution is a equation, or a, the solution is either an equation or a graph in here, or a family of them, if we're talking about a general solution. So I without the equals c, I don't really, you're following a procedure. It's like you've been here, you've seen things I've done, that's great, but equals to a constant is the solution. Like all the x, y that solves, this is the solution. Okay, but anyway, those are standard errors, so you guys are well within norms for this course. Like, no particularly new errors were made. It's good. Well, it's kind of disappointing. Sometimes I want to see some new errors, but I shouldn't say that. I'll regret that. So section 2.5 in my notes is physics and applications. And so in this, I point out some kind of like perhaps obvious things, namely that most of physics is solving a differential equation, right? Like you already got it. Okay, cool. So we have the net force is equal to mass times acceleration, or you may remember we eventually retraded that for the change in momentum per time, right? dp dt. And so if we're given a net force, which is either, which is actually a function of velocity or function of position or a function of momentum, whatever, then solving Newton's equation amounts to solving a differential equation, right? Now, admittedly, if we solve for position, it's a second order differential equation, right? Because ma, the position is a function of time. That gives us a second order problem. And we haven't solved many of those yet, right? I think we solved one of them one day by guessing. Remember? We ended up with like y prime prime equal to minus y, and we're like, sine will do, right? We'd like to derive that at some point in here, which I'll get back to eventually. Probably not today, though. So here's some common forces like spring force, force of gravity, the better force of gravity, thanks Newton. A thrust force on a rocket, right? That's a problem where the mass is variable, right? That kind of problem maybe you didn't solve in physics 1, unless you had Bouderi's, in which case you probably spent 2 weeks solving it, but which is cool, which is awesome. I love Bouderi's. How many of you guys want a residential physics major? Nobody? Raise your hands higher so I can see them. 1, 2. All right. 1, 2. Any more? No? We got 30. So that's 2 out of 15. Let's see here. Let's inflate the number. There's like, so it's about 10%. How many engineers are there here? No, not here. Like the university. How many we got? How many hundreds of you? Between 500 and 600? So if we had 10% of you guys also double major in physics, it'll work. All right, we need a physics major. It would be good for you guys to have a physics major you could sample higher courses from, honestly. Okay, so anyway, I digress. Who knows, maybe that'll happen. So we've worked this problem, right? A velocity-dependent friction force. We've worked n equals 1 and n equals 2 in here. And then, of course, you could also have an external force, right? You could have a mass, and you're like doing something like this. if I could do that more smoothly, that would be a sinusoidal force, right? How do you solve those things? They're all differential equations, all right? Here's a short derivation. If your force is just a function of x in one dimension, then it's a conservative force. And as such, you can, well, anyway, this is just the work energy theorem. It says that the change in kinetic energy is equal to the work done by the one-dimensional force. If that force is equal to minus du dx, then we get conservation of energy. I'll take 10 minutes to derive that in 3 dimensions, like a future class probably. All right. So here's another derivation that if your total force is conservative, then we have conservation of energy, which is say that the energy doesn't change with time. Now, this is not what I'm after today. Let me skip ahead here. So here's one. Suppose you have x as the position of a mass undergoing one-dimensional constant acceleration motion, initial velocity v naught, position x naught. So, all right, what am I trying to do? I'm trying to find how the initial velocity and well, I can't read my own writing. You find how the initial and final velocities and positions are related. All right, great. So I do my acceleration is v dv dx trick, which gives me that this constant acceleration a times dx is equal to v dv. Integrate both sides, and we get the so-called timeless equation from physics 1, right? So the v dv dx trick allows us to derive this hopefully well-known equation to you from, well, really from high school physics, honestly. Here's another problem. Suppose you have population growth, and the population grows at a rate which is proportional to the population. This is so-called exponential population growth, right? So dp dt is kp. How do you solve this one? Well, separate, integrate, and lo and behold, exponential growth, right? In my undergraduate, I saw this in like 4 separate classes. It's like every class is like, and they each spent like a whole day on it. I was just like, enough already. So I spent 10 seconds. I hope you're happy. Anyway, to spend longer is to bury you in boring numerical stuff for that problem. You know, who wants to see that? This is an example only electrical engineers will love, but here it is. So if you have the voltage dropped across a resistor, and you also have a capacitor involved. So I think this is a resistor and a capacitor in series. You end up with the voltage dropped. Let's see here. So this is the voltage across the resistor. This is I times R, Ohm's law. And over here, Q over C is the voltage on a capacitor. So if you just have an RC circuit, this is the Kirchhoff's voltage law that you get, which again is a differential equation, in this time in the charge. Separate, integrate. You find that the charge as a function of time is equal to the initial charge on the capacitor times the exponential e to the minus t over RC. RC, we usually call it tau in physics or engineering, which is the time constant, right? After about 5 time constants, the capacitor is completely discharged up to about 99%. After the first time constant, it's only got like 37% of the charge left. So a time constant is essentially the time scale on which an RC circuit is active. Here's a one that's a little bit more geometric in nature. This is kind of a more adventurous question, which is to find a family of curves which are increasing whenever y is less than minus 2 and y is greater than 2, and they're decreasing between minus 2 and 2. So I came up with this differential equation, y plus 2 times y minus 2. So that's like a parabola in y. And so parabolas go like this, right? So between the intercepts, it's negative, which means decreasing slope. And over here and over there, it's positive, which means increasing slope. So it's easy to check that this formula gives you positive beyond plus or minus 2 for y, and it gives you negative between plus or minus 2 for y, which is what I wanted. Now you might say, well, aren't there other functions which do that? Well, sure. I'm just trying to find one, though, and let's not make it more complicated than it needs to be. And so can you solve this differential equation? Well, sure. Yet again, separate, and integrate, right? And partial fractions, later, we get this. You do need partial fractions for the homework, right? I hope you found that out. At least one problem. And so there you go. I think I might have a picture of this. So here's the actual, and I'm going to try to show you guys, this is p-plane. P-plane is a thing you can put in MATLAB. You might have to download it from like the file exchange or whatever. But p-plane is super useful. It will allow us to plot solutions and to first order differential equations. We can gain much understanding from p-plane. I'll probably talk more about it next class. But as you can see, these solutions are increasing down here. They're decreasing here, and they're increasing up there, just like we want. Now, this kind of mathematics you'll find in something called logistic growth. So, orthogonal trajectories of x dx plus y dy. That, I think, we just worked earlier today. Find orthogonal, but this is a little bit different. Notice the format of the problem here. Find orthogonal trajectories of x squared minus y squared equals to 1. What's the difference between that and problem 1 on the quiz today? Problem 1 on the quiz, I gave you a differential equation, right? Here I gave you a curve. How do you find the differential equation which this curve satisfies? This is actually a much easier question, right? You differentiate. So you do implicit differentiation a la calculus 1. So dy dx, like 2x minus 2y dy dx equal to 0. And then that gives me dy dx equals x over y. Find the orthogonal trajectories. Negative reciprocal, right? Minus y over x, integrate. And we get these lovely reciprocal functions. So the x squared minus y squared equal to 1 is a hyperbola which opens, which way does it open? Oi. I gotta think about this for a second. If I put y equal to 0, I get no solution, so I get x plus minus 1. X plus or minus 1. So I think this one opens sideways. Like, so the x squared minus y squared equal to 1 is like this guy. And what I have graphed is much more than that, right? So, but another example here. Well, this one we just worked out, yeah? We worked this out today. It's good. I found the same solution. That's a good sign. Newton's law of cooling, another interesting question. It says that the rate of change of the temperature is proportional to the difference in the temperature and room temperature. So this problem has two constants. The one is the proportionality constant, the other is room temperature. So to solve a Newton's law of cooling problem, you actually need 3 pieces of data, because you need like an initial temperature, you need the proportionality, and you need room temperature. So there's 3 things, you need 3 pieces of data to solve a Newton's law of cooling problem. Let's see here. But the actual mathematics there is separation of variables. Let's see here, I'll show you one other here. Let me skip ahead. This is a mixing tank problem. People work these. I'll probably work one another day. The one I wanted to show you before I let you go. Oops. I'll find it eventually. This one. This is a dastardly problem. Suppose a flexible rope of length 4 foot has 3 feet coiled on the edge of a balcony and 1 foot hangs over the edge. At t equals 0, the rope begins to uncoil further, and then you're supposed to find the velocity on a rope as it falls. And how long does it take for the rope to fall completely off the balcony? Assume the force of friction is negligible. So the force of gravity is mg, and here we have dp dt, right? But the thing is, the mass is changing, all right? So like, because it's the mass that's hanging off that is the part that's moving. The part that's coiled on the desk is not moving yet, you know? So you can trade m times v for lambda x. So lambda is the mass per unit length, x is the length hanging off. And that gets me to this, which gets me to this monstrosity. And this differential equation is actually rather nasty. this one I actually had to solve using the special integrating factor techniques that I don't cover in here. But anyway, it can be solved, and there it is. So I just want to tell you guys, we can solve variable mass problems. We can solve all kinds of problems using the calculus and techniques I'm showing you. And I just wanted to make you aware of that. So next time, we'll talk about the direction fields and the theory of differential equations. I'm pretty much exhausted what I have to tell you about solution techniques. So just so you know, for first order problems at least.